welcome you, Dr. Sangita. So you please start your talk of today's webinar. Thank you so much for finding out your time for this talk.
Thank you, ma'am. Thank you for inviting me and giving me an opportunity to interact all of you. Today, I'm going to talk about one of the finite element method known as the hybridizable discontinuous Galerkin method. So, before starting, let me tell you about some introduction of that. So, I would like to know, is there how many of you are here who works in the field of numerical analysis for PDE, so that I can get the idea what's how the audience, undergraduate, postgraduate, or PhD students?
See, Dr. Sangita, only here mostly people are working on fluid dynamics and etc. partial differential equation. But in this webinar, some research scholars also joining. They are also joining, and in addition to our faculty members. So accordingly, you can proceed.
Okay. Thank you, ma'am. So the discontinuous Galerkin method is one of the finite element method. Finite element method is a numerical method through which we get an approximate solution of a partial differential equation. We can apply it to the ordinary differential equation as well. But when it is difficult for us to find out the analytical solution, we go for the numerical methods, and this one of numerical method which I'm talking about is finite element method is going to be a tool to find out the approximate solution. So these discontinuous Galerkin method for partial differential equation allows us to take discontinuous solutions in the domain. So for example, suppose you have a differential equation and you are interested in finding a solution for the differential equation which is going to be continuous in nature. So first we divide the domain into subparts, and then we construct some basis functions locally. We make it a global basis function. We construct the functions, and then we proceed by solving a linear system of equation. But when we are dealing with a discontinuous Galerkin method, we just relax with the condition of continuity. We don't impose the condition of continuity on the approximate solution. But what we prove that as we continue to refine our domain, we are going to approach towards a continuous solution. Okay. So the outline of this talk is going to be as: first, we'll discuss about some motivation for these methods, literature review. Then I'll discuss the hybridizable discontinuous Galerkin method for a Poisson problem, and we'll demonstrate the numerical result of this method. So this discontinuous Galerkin method was first studied by Reed and Hale in 1973. That is for hyperbolic neutron transport phenomena. But it didn't get that much popularized. So, and after 1973, it was shown in mid of 80s who discussed this discontinuous Galerkin method for nonlinear hyperbolic problems. So generally, we know that if you talk about the Taylor series expansion, and if you just truncate the Taylor series, we get a polynomial. And you know that if you approximate a function by a polynomial, let us say by degree k, then we expect that rate of convergence is going to be of order k plus 1. Similar thing we also expect it here. Suppose we are approximating our solution by a polynomial of degree k. In that case, we expect that we should get rate of convergence as k plus 1. So, but what was happening in this late 90s, whenever it has been done, so we were having two quantities. One is going to be the solution, another one is going to be its derivative. So if you are dealing in multidimensional problems, so this derivative is going to take the form gradient of phi. So if you approximate this solution u by a polynomial of degree k, so let me denote that pk denotes the polynomial of degree at most k. And if you approximate this grad u also by a polynomial of degree k, it was no use, because here you were having the rate of convergence as of order k plus 1, but for grade U, it was only of order k. It doesn't matter whether you choose a polynomial of degree k or k minus 1. So people were using, instead of pk, we were approximating the polynomial of degree k minus 1 as there was no change in the rate of convergence. So to avoid this case, like if we are doing the approximation by polynomial of degree k, we should expect this as a k plus 1, but it was not happening. So later on in 2000, so let me go forward. Yeah. So it is here. So in 2000, this Castillo is there who could prove that with the analysis, he just modified the analysis and could prove that there is of order k plus half for the gradient one. And now it motivated scientists that if it is k plus 1 half, so there is a scope to improve further. In 2008, it was Cockburn who could prove that yes, it is possible to have rate of convergence as k plus 1. He could also propose a post-process solution, which is going to be based on the approximate solution or DC solution, but having the higher rate of convergence. It was having the higher rate of convergence. So that was the motivation to study this STG Galerkin method. So there is going to be flexibility in local mesh adoption. For example, like when we have the finite element method, we cannot allow the hanging nodes, but here in DC methods, you can allow the hanging nodes. You can choose different degrees of polynomials in different subdomains. So we say that it is easy to handle non-uniform degrees of approximation. And it can have good accuracy even if the solutions is not sufficient smooth over the computational domain. And the method is going to be element-wise conservative. So in 2000, there's Arnold have proposed a unified framework for the DC method. So where he discussed about interior penalty method, this we call symmetric Galerkin interior penalty method, and the non-symmetric interior penalty Galerkin method. So later on in 2004, Bastinza proposed this DC method for nonlinear elliptic problems, and it has been carried forward by Goody in 2007 and 8. Goody has also proposed these LTC methods for nonlinear elliptic problems. So what is happening in LTC method? It is like a fluxes which we have, it is going to be chosen in such a way that you can remove one of the variable. So that's what, like, which I discussed, that in 2008 Cockburn could prove that for gradient we can have the rate of convergence as k plus 1, and they called it as a super convergent DC method. Later on, this Cockburn and his group carried this work for heat equation and the wave equation, and they observed that similar thing also holds true for heat equation and wave equations. In 2013, I carried forward this work for non-self-adjoint and indefinite elliptic problem, which was the motivation to get the error estimates for quasi-linear problem and non-linear problem. Recently, in 2019, we could also observe the same behavior for non-linear parabolic problems. So these discontinuous Galerkin method which I'm talking about, these were like very easy to implement for linear problems, but it was some complications for the nonlinear problems. But this has been analyzed during 2013 to 2019. So, however, these Daisy methods for second order elliptic equation have been criticized because for the same mesh and same polynomial degree, the number of globally coupled degrees of freedom of the DC method is much bigger than those of the continuous Galerkin method. What does it mean? Like, suppose I have the square domain, and let us divide it into subtriangles. So here we call these are the node points, and then these triangles which you can see, these are known as the elements. So when you are having continuous Galerkin method, in this case the degrees of freedom is going to be only 9. So you need to solve it 9 by 9 size of 9 by 9. Okay. But when you talk about the discontinuous Galerkin method, suppose you are using linear polynomials. So in this case, you are supposed to solve 8 into 3. That is, it is going to be 24 by 24. So size of the linear system of equation is going to be 24 by 20. So if you increase these elements, the size of the coefficient matrix or the size of the system is going to be increased. So there is going to be very costly these methods because of the big size, but with the same output. So to overcome this one, these SDG methods have been introduced, where you will need not to solve this large system of equation, but you can get this higher rate of convergence, which we call as the super convergence, by solving a smaller system of equations. Okay. So that is. So the main feature of these SDG methods are that these can be obtained by discretizing characterization of the exact solution written in terms of the many local problems. So local problems are going to be defined only element wise, and in terms of, and we will be solving a single global problem whose size is going to be much smaller in comparison to the standard DC methods. This permits an efficiently implementation since they inherit the above mentioned structure of the exact solution. The SDG method can be used for steady state problems and time dependent problems when implicit time marching methods are used. So it is because like these methods are going to be stable unconditionally, while explicit methods sometimes turns out to be unstable or even conditionally stable. So it is not a good idea to use explicit methods to solve the time dependent problems. So what we do, we define the local solvers by using a Galerkin method. Oops, I'm sorry. Okay. For devising the method, we follow the following guidelines. What is that? We use a characterization of the exact solution in terms of local problems and the transmission condition. Transmission condition is which we call as a continuity condition. Okay. And we use discontinuous approximation for both the solution inside each element and its trace on the element boundary. We define the local solver by using Galerkin method to weakly enforce the equations on each element, and then we define a global problem by weakly imposing the transmission condition. Okay. So this is how we are going to work on the DC method. So let me demonstrate this using a model problem. So here I choose this elliptic equation CQ plus gradient of U equals to 0 and divergence of Q equals to F in omega, along with the condition that this U hat takes the value as a UD on the boundary of omega. So please make a note that this hat notation has been used for trace of U. Trace of U means the boundary, the function value on the boundary. So here, this problem is second order differential equation of the form A grad U equals to F, where we assume this A to be strictly positive and bounded below. Let us say that this constant is alpha naught. So for this problem, we introduce a new variable. Let us call this vector Q, which is going to be nothing but minus of A times gradient of u. So if I substitute over here, this is minus over here. So this problem is going to take the form as divergence of q equals to f. But if I just take simple manipulation over here, that is minus 1 by a q plus gradient of u equals to 0. If you choose this a as the function c, you will get the first equation and the second. So here what we actually do, we were having the higher order differential equation, we have reduced it to a system of first order differential equation, and that is known as a mixed method. We are having two variables u and q, where one is known as the primal variable, another one is known as the dual variable. Okay. So since the condition which we have, it is true in the domain, so it is going to be true on the subparts of it. So what we do is, suppose we have a domain, so we triangulize it by, let me denote this as tau h, which is going to be collection of the triangles such that union of all these triangles is going to be nothing but omega. These triangles are element wise disjoint, and you can allow the hanging nodes as well. So since the equation is true in omega, so it is going to be true for each element, and that's what we call as a local problem. But then what we need, that since we are talking about this discontinuous, so in each element we are going to talk about this discontinuity. So here, like yeah, let me take it like this. Let us consider these two elements. I am having one as k1, another one is k2. So this jump is nothing but, let me write it down, jump of for any function u. So this is defined as u hat restricted on k1 minus u hat restricted on k2. So you can see the difference of the values on the elements. So what we need, that this function, whatever we are computing, this u hat, which is stress, it should be single valued function. So it should take the same value if you are coming from k1 on the boundary of this triangle, or it should be coming from the triangle k2. That's why we have the jump of u hat, the trace of u is 0 on each phase. So here epsilon h is this epsilon h 0 is giving you collection of all the a's, so that E belongs to boundary of k for k in tau h. For k in tau h. So we require that on every edge, the jump of these functions is going to be 0, whatever you calculated. Okay, these one. And similarly, for the function q, jump of q hat should be 0 on all the interior faces, and that we call as the transmission condition. Okay. And then we will require this u hat to take this value, which is given to us ud, for each edge on the boundary of the domain. So E is nothing, this epsilon h boundary is nothing but collection of all the edges which belongs to the boundary of k intersection boundary of omega for some k in the triangulation tau h. Okay. So is somehow the idea is clear how we are going to the local problem and transmission condition? If so, then I can proceed further.
Yes, yes.
Okay. So now we rewrite these equations as find u and q in each element k and u hat on the boundary of k such that you get, or you can say u, q and u hat satisfies these three equations. Along with these transmission condition on this, so jump of q hat is going to be 0 on the interior edges, and u hat is going to be equals to ud on the boundary of edges, where this q hat is the trace of the function q, which is going to be dependent on the trace of u and the function f. It is going to be dependent on the trace of u hat and F, because from here you can check it out. Like you can see that this U hat is going to be dependent on F, and then Q hat we are making dependency on U hat and F. So let me write down the weak formulation of these problems. So what we do, we take a function W, multiply it in the first equation. So let us take multiply W, a function which is going to be L2, and integrate over omega. For the second part, that is gradient of U multiplied with W, use integration by parts, and you are going to get something of this form. And similarly, just multiply by a function V in the second equation and use integration by parts to get the second equation. And then we will be using this transposition condition that we require, that the trace of Q, the normal component of the trace of Q is going to be same as the normal component of Q on the boundary of K. So using these conditions, we will end up that we can choose UH, QH, which are going to be some polynomial functions in terms of two functions, which is going to be UH hat and F. And then you will solve these two equations. After finding this UH and QH in terms of UH hat and F, you are going to substitute these values over here for QH and UH in terms of UH hat and F. This will give you a global system of equation if you do it for all. And then we will solve this system of equation only for UH hat, not for all the variables U and Q. So what is happening here actually, if we solve globally this system of equation, the size of this system is going to be much smaller than the compared to the standard DC method. And then we will be solving this system of equation locally, which has very small size. It is going to be like what I say, very small in comparison. It is going to be simply 9 by 9 if you are using this linear polynomial. That's it. Okay, so this locally you can solve it very easily because it is going to be a small system. But if you go for the DC method, you try to get the solution over here, it is going to be large comparatively. So here, the local solver on K, that means these UH and QH are going to be well defined if you choose this tau. What is tau here? This we call as the stabilization parameter, which we are choosing constant element wise. On the boundary of K, we will be choosing them as a constant. And this stabilization parameter plays a very important role in the analysis of HDD method. So I'll just skip the proof, but the main aim is here, like if you impose this condition for all faces on the interior edges, and then they impose the boundary condition for the trace of U, this is going to be your global problem. Whose size is going to be much smaller than the standard DC method. And here happens that if this numerical trace UH hat is well defined, if you have that, whatever space you are choosing, that means V and W, we are choosing these spaces and we are taking these functions when we are talking about these formulations V and W. So V we are taking from the space Vk and W we are choosing from a Wk. So we need to choose these spaces so that this condition is being satisfied. That is, gradient of V is going to be contained in the space of W. That's condition we require to have the trace to be well defined. Otherwise, there may be a problem while solving this system of equation. That system of equation may not be consistent. So to make it consistent, we require that gradient of V should be contained in W. So what these spaces you can choose. So the spaces for these choices for these spaces is like for W, you can choose the Rabiat-Thomas element. It is going to be polynomial space of the form pk plus xpk. So you can say that this space will be contained in pk plus 1 and will contain space pk. So it is not exactly pk, not exactly pk plus 1, it is in between. So degrees of freedom here is going to be less in comparison to the pk plus 1 and going to be higher than pk. And if you choose like this one, space V, we will be choosing as set of the polynomials. So pk, let me explain what pk is. Pk denotes the set of polynomials at most degree k. Set of polynomials at most degree k. So from this space M, we will be choosing our numerical trace. So we are also choosing that it to be a polynomial of degree k. So the choices for this is possible if I choose k to be bigger than or equals to 0. But you can also go for BDM elements. That means you can choose W to be a polynomial of degree at most k. V, you can choose a polynomial space of degree k minus 1. And M, you can choose as a polynomial space of degree k. So this choice will going to give you this superconvergence provided you choose polynomial degree to be bigger than or equals to 1. If you choose like a P0 here and P1 and P0, in that case, you may not achieve the superconvergence, or post-process solution may not give you the higher rate of convergence. In STZ method, we are going to choose WK as a polynomial of degree k, VK also a polynomial of degree k, and in PK, this M we will be choosing, and here you can choose k to be bigger than or equals to 0. So you know that this STG method is going to be better than the BDM method, because here you can allow k to be 0 as well. While in continuous Galerkin method, we use WK to be PK minus 1 and VK to be PK, and this MF you can choose as a PK. Okay. So these are the choices for the spaces W, V, and M. So here I'm going to tell you what this stabilization parameter affect the analysis. So when we choose this Raviat-Thomas element, that is, in that case, our stabilization parameter tau is going to be 0. Rate of convergence for the solution is going to be k plus 1, and for QH it is also going to be k plus 1 for all k bigger than or equals to 0. So here you can see that Raviat-Thomas elements are going to give you the superconvergence result, but here you are going to have this space RT, you know that it is going to be bigger than PK. Okay, so you are paying something to get k plus 1. Same thing for the BDM, but here what is happening? BDM we choose PK. The rate of convergence for the solution is only k, not k plus 1, right? So you can say in the RT method, you get higher convergence than BDM method. And as well as this BDM method holds true only when k is bigger than or equals to 2. This rate of convergence which you are having k plus 1 may not be achieved when you choose k to be 1 or 0. But when you are doing this HTC method, and if you choose the stabilization parameter to be of order 1, that is constant, in that case, we are getting rate of convergence in UH as k plus 1 as well as k plus 1 in QH for all k bigger than or equals to 1. And here you also have the post-process solution, which will have rate of convergence as k plus 2. It converges faster than UH. But if you choose this stabilization parameter of order H, then rate of convergence in the solution is only k. It is not k plus 1. But in QH, you will be having k plus 1. On the other hand, if you choose this stabilization parameter of order 1 by H, then you will have k plus 1 in the solution UH, but in gradient, you will lose. It is going to be only k. And if you choose the stabilization parameter to be of order 1, and if you choose the degree of polynomial to be 0, in that case, you are able to see the superconvergence for UH and QH, But here you will not be able to get superconvergence for UH star. It is going to be only of order H. So that's the reason we suggest that the best choice for the stabilization parameter is going to be of order 1 on each element, and you can choose this as a polynomial of degree k, and you are going to get the rate of convergence for UH and QH both same with k plus 1, and you are able to get one post-process solution UH star, which is going to be of order k plus 2. So that's the reason that why this SDG methods is being now celebrated very much, because of higher rate of convergence in QH. Now, like how we are going to get this post-process solution? So for post-process solution, this post-process solution is not going to be very costly for us, because we will be computing this by solving the local problems based on our computed solution QH. So we try to find out a solution UH star, which is going to be in a space V star, which we choose a polynomial of degree k plus 1. Okay. And we require that our solution UH star satisfies that gradient of UH star comma gradient of V equals to minus CQH comma gradient of V on for every element in K. And then we also require this condition that UH star has the same mean as your solution UH over each element K. In that case, this U minus UH star, that is error in the solution, is going to convert faster to 0 than the error U minus UH. So that's what we say, that higher order convergence. Here you are going to get K plus 2, and here you have K plus 1. Okay. So that's what all about the SDG method. So what are the advantages of the SDG method? We can solve a much smaller global system of equation in comparison to the degrees of freedom which occur in discontinuous Galerkin method. And then we can solve for the solution local problems. We can get this post-process solution, which is going to be having higher rate of convergence than the SDG solution. So let me demonstrate this using the numerical methods. Yeah. So here, just for this demonstration, we have chosen omega to be a square domain, and we have chosen this f in such a way that the exact solution turns out to be cos pi x, cos pi y. So for this, we compute the solution using linear polynomials, choosing the stabilization parameter is 1 and the mesh size h as half. Okay, so in that case, here you can see this is going to be your exact solution. This is your UH, that is which we have obtained by solving local problems. And then here you have the post-process solution UH star. So you see that the H is going to be large. The degree of polynomial is also not very high. We are just using linear polynomials, but still one can easily compare UH with U and UH star with U. And you can see that UH star seems much closer to U in comparison to the UH. And that is because of higher rate of convergence. So error in this quantity, you can say that it's going to be smaller than the error in UH. Similar thing, like if you just see, if you decrease this mesh size, you can see they are almost comparable, right? So convergence you are able to see with as h goes to 0, the solution is approaching towards the exact solution. And similar thing you can observe for quadratic polynomial and the cubic polynomial. Okay. So here I have not plotted the rate of convergence, yeah, but we have the tables where you can see that for linear polynomials, rate of convergence is 2 for UH, 2 for QH, and 3 for post-process solution UH star. And similar behavior has been observed when we use the quadratic polynomial or when we use the cubic polynomial. One can extend this for 4th degree polynomial, but it may take some time to do that one. Okay. So now I have this list of the references for you. So you can read this paper where they could prove k plus half for the gradient, and then you can go for this one. Yeah. Superconvergent easy method for second elliptic problem where they have proved it to be k plus 1. Other are the related references. If you are very much interested, you can go through these references. Okay. Thank you for your attention. Please feel free to ask any doubt.
Yeah, any questions from the participants, please?
At least those who are working on finite element methods, they could have followed something.
Yeah, any questions?
Yeah, no, ma'am, because the thing is that people are not working in this direction.
Okay,
some
so
of the students, some of the students are only focused on this continuous Galerkin method. So might be the recent joined students might be work on that direction.
Yeah, this like these methods are very much open. It is they like researchers are finding it difficult to apply for non-linear problems. So one can take it forward for like Kirchhoff problems and these non-linear wave equations. There is so much to do.
Yes.
Yes.
Parabolic type Kirchhoff problem, elliptic type Kirchhoff problems.
Parabolic type Kirchhoff problem, they are like
Hello.
to manage.
Okay.
Yeah, sister, do you want to speak anything?
Hello, ma'am. Am I audible?
Yes, you are.
Like, yes, ma'am. Like, suppose we are dealing with some nonlinear fluid problem, then can it be possible to solve with this kind of Galerkin approach? Because there in fluid problem, we often do the finite volume. So,
Solving the
the
non-linear
advantage
system
of this
of
finite
equation.
volume is we can use the corner the nonlinear type of equation. Say basic equations. If you say Navier-Stokes type of equation, there is the convective term, this kind of thing. So can it be tackled with this
Yeah,
Galerkin
it
approach?
has already been studied for Stokes problem. Some study has been done. You can find it out. Even this group of Cockburn and Shrew have studied these Stokes problems for DC methods.
Stokes problem can be handled, that I know, because Stokes problem there they have omitted the nonlinear part, this convective part. But if I include this convective part, that means you dot grad u, that term. So can then it be handled with this Galerkin approach? Because often we see that when we're dealing with this nonlinearity, we are solving this by some numerical approach. So can it be helpful for this kind of thing can be tackled with this Galerkin method?
Most probably, because if you just recall this, in the late 90s or it's the late 80s, this C.W. Shrew along with this Cockburn have studied the nonlinear hyperbolic problems, this transportation problems. Okay, so you can find out this Cockburn, some research on Navier-Stokes equation.
Okay, ma'am.
I have not explored these type of equations, but I'm sure there is some literature on Navier-Stokes equation by Cockburn for DC methods.
Okay, ma'am. Thank you.
Yeah.
So it was a very nice presentation, Dr. Sangita. Thank you so much for joining us for this webinar. And now I request Mr. Santosh, to offer the vote of thanks from our department as well as from SOAWAL University. Dr. Sant. Mr. Santosh. Thank you, Dr. Sangita. Thank you, Santosh, and thank you, Dr. Ambit. Thank you, everyone.
Thank you, ma'am.
Okay. Let us wind up
Thank
this.
you.
Yeah.
Yeah, sure.